Hello, everyone. Thank you for taking the time to watch my talk. I want to start by thanking the organizers for inviting me. And so I'll be talking about Stein fillings of universally tight contact structures of LPQ and classifying them up to symplectomorphism. And so this first talk will be just sort of the background and motivation for that, and we'll end with the result that we'll be using to start the second talk, where I just talk about my results and how to compute them. So yes, this is part one, the big picture talk, and we'll begin with some of the basic definitions. So a contact structure on a three manifold is well, you start with a plane field, which is a subbundle of the tangent bundle, where when you intersect the plane field with the tangent space of M at point P, that's a two-dimensional subspace of TPM. And then your plane field is a contact structure if it's the kernel of some one form alpha, where when you take alpha wedge d alpha, it's non-zero, and that alpha can be defined globally or locally. So what I have in the bottom here is our standard contact structure on R3. Sometimes we just denote R3 and then standard. And so as you can see, the contact planes are flat, parallel with the XY plane when you're going along the Y-axis, but then when you go further out on the X-axis, either direction, they kind of twist counterclockwise. And this contact structure is important because Darboux theorem tells us that any contact manifold is locally the same as R3 with the standard contact structure. So there are a few kinds of contact structures we want to define. Contact structure is over-twisted if there exists an embedded disk whose boundary is tangent to the contact structure. So we say that its boundary is Legendrian, and it has the foliation like these. And so what's going on here is the intersection of the disk with the contact planes gives you these foliations where you have singularities at the center and on the boundary of the disk. And those singularities are the ones where the contact structure, the contact plane at that point P, is equal to the tangent space of the disk at a point P. And then as you go along these foliations, the contact planes twist, and then they're twisting along the foliations, and then they've completely turned over once they've hit the boundary. So again, there's singularity. So again, at the boundary, the contact plane there is equal to tangent space of the disk at that point on the boundary. And the way that you can get that second disk that I have here from the first one by just keeping that boundary of the disk fixed and then pushing up on the interior a little bit, and that's going to make the foliations start twisting like that. So this contact structure, which we usually denote OT, is equal to cosine R dz plus R sine R d theta. So yeah, that's the over-twisted contact structure. And then a tight contact structure is one where there is no such over-twisted disk. And then a contact structure is universally tight if the contact structure is still tight when you pull back to the universal cover. And so R3 with the standard contact structure is tight. And so Darboux theorem tells you that tightness is a local property, that all contact structures are locally tight, and therefore over-twisted is a global property. All right, so contact structures are the odd-dimensional analog of symplectic manifolds. So for a symplectic manifold, that's an even-dimensional manifold where you have a non-degenerate 2 form that's exact, and when you take the wedge sum with itself n times, it's non-zero. And the standard symplectic form for R2n is dx1 wedge dy1 plus dx2 wedge dy2 plus ... plus dxn dy wedge dyn. And so that's in the coordinates x1, y1, x2, y2, and so on, up to xn, yn. And just like for contact structures, we have symplectic Darboux theorem, which again tells us that all symplectic manifolds locally look like R2n equipped with the standard symplectic form. So we care about symplectic manifolds whose boundary is a contact manifold, and we're going to define a couple of those. So if you have given a contact structure and a symplectic structure, a contact structure on M is strongly symplectically filled by your symplectic manifold if X is compact and its boundary is M. And then you have this vector field that we call Liouville vector field pointing out of X along M, such that its Lie derivative is a positive multiple. The Lie derivative of your symplectic form along V is a positive multiple of the symplectic form. And then interior multiplication of omega with V, that turns your 2 form omega into a 1 form. And it's strongly symplectically filled if that interior multiplication is a contact form. So its kernel is equal to the contact structure. So there's a special kind of strong symplectic filling that we want to define. First, we're just going to go over handle bodies real quick. So a handled body decomposition is of a manifold is when you can construct the manifold using these n-dimensional K handles. So an n-dimensional K handle is just dk cross dn minus k. And the way you construct it is you attach your K handle to the boundary of the manifold along the attaching region, which is what I have in this picture I've highlighted in blue here. And so the attaching region is just the boundary of the first factor dk cross dn minus k. So that's going to be sk minus 1 cross dn minus k. So this is like a 2-dimensional picture of a 1 handle. And so the core is dk cross 0, which I have in red. And then the co-core is 0 cross dn minus k. And in dimension 4, your 2 handles are d2 cross d2, And the attaching region, sorry, I should write H2. The attaching region is going to be the boundary of D2 cross D2. So that's going to be the solid torus S1 cross D2. And so in order to specify the attaching region or define the attaching region, you need both the knot that you are sort of embedding this solid torus along, and then also a framing on the knot. And so a strong symplectic filling with a handle decomposition of 0, 1, and 2 handles with a framing equal to the contact framing minus 1 is a Stein filling. And so the way that we define a contact framing is, which is also called the TB invariant, the Thurston-Bennequin invariant. So given a knot L, L is Legendrian, so that means that it's tangent to the contact planes. And what you can do is you can define a vector field that is along L. So define a vector field on L that is nowhere zero and transverse to the contact planes, like so. And then you can push the knot off along this vector field, where you can think of it as connecting the arrowheads of the vector field. So maybe it looks like this. And so that'll be your new knot, called L prime. And then the contact framing, which we can call the TB number of L, will just be the linking number of L with its push off. So the point is that you are attaching the two handles along Legendrian knots whose framing is that contact framing minus 1. And so the way they're defined, Stein fillable contact structures are strongly fillable contact structures, and also strongly fillable contact structures are all tight contact structures. So we have this inclusion here. So that brings me to the problem that I'm looking at, which is, can we classify fillings of LPQ spaces or lens spaces equipped with a universally tight contact structure up to symplectomorphism? So here's what's been done so far in terms of classifying Stein fillings of LPQ. So remember that LPQ is obtained by doing negative P over Q surgery on the unknot in S3. And in 2008, Liska classified all fillings of universally tight contact structures up to diffeomorphism. And so if you look at this first example, there's actually a formula for the TB invariant, that it's going to be the writhe of the knot minus the number of left cusps. And so in this case, that's going to be 0 minus 3. So you get -3. And of course, LPQ is, again, obtained by doing, well, in this case, L41 is obtained by doing -4 surgery on the unknot on S3. So you're attaching a 2-handle along that unknot with framing -4, which is the contact framing of this knot, -3 minus 1. So that checks out. And then next in 2020, at Nair and Roy, and then independently Christian and Lee, classified all fillings of contact structures of LBQ up to diffeomorphism. So here's one non-universally tight contact structure on L41. And then our goal, well, naturally, we want to also think about the symplectic structure of these fillings. And so naturally, we would like to upgrade from diffeomorphism to symplectomorphism. So in order to do this, we're going to use a result from Wendell that uses planar open books. And planar here means the disk with a certain number of holes removed to classify Stein fillings up to symplectomorphism. So without further ado, let's move on to abstract open books. So for an abstract open book, you just need two pieces of data. One is a surface with boundary, and then the other is a map from the surface to itself. That's the identity near the boundary. And we call this the monodromy. So what you do is you take the mapping torus of the surface with this monodromy. So that's going to be surface across the interval where you identify phi of x0 with x1. And then you take that, and then to make your open book, which we've denoted m phi, you glue in solid tori. You glue in one solid torus for each boundary component on the surface. And so what this map does specifically is it identifies the boundary of the solid torus with your boundary component of the surface across S1 by sending the meridian of the boundary of the solid torus to some point Q prime in the boundary component L across 0, 1 with the endpoints identified. And then it sends the longitude S1 cross P to the boundary component L. Okay, and so as an example of this, we have the abstract open book for S3. And so your surface is an annulus, and then your monodromy is just the Dane twist about this curve C. So remember, the Dane twist is just, it's a positive, for this talk, these are positive Dane twists, which are right-handed Dane twists. So that means that it's sending this arc right here, this purple arc, to this arc by doing a 360 twist on it. All right, and next we just need to define positive stabilizations. So that's when you do a positive stabilization of an abstract open book, you take the old page, sigma, and you make a new one by just attaching a one handle. And then, so that's your one handle, and then here's the co-core of the one handle. And your monodromy is just going to be your old, your original monodromy composed with a Dane twist about some curve alpha that is intersecting the co-core exactly once transversely. So you could have this be your alpha. That's one positive stabilization. You could also have it go around here. But the point is that it's just, you attach a one handle, and then you just make sure that you do a positive Dane twist about a curve that's intersecting the co-core of the one handle exactly once. And so with this information, we can state important result of Giroux, which connects kind of the geometry and the topology here. So if you have a if you have a closed oriented 3 manifold, then your oriented contact structures on the manifold are in one-to-one correspondence with open book decompositions of the manifold up to positive stabilization. So we're going to use open books to classify Stein fillings of contact structures on LPQ up to symplectomorphism. And so in order to get from your Stein filling to an abstract open book, we're going to use Lefschetz vibrations. And so given a oriented compact 4 manifold, a Lefschetz vibration on X is this smooth map from X to a surface. It could be any surface, such that you have a finite number of critical points where around each critical point you have these orientation preserving coordinates. So you think of CI as in C2, and then 5CI is in C. And the map pi is given by taking two complex numbers and then sending it to the sum of their squares. So the picture we draw is like this. And like I said, this can be, a Lefschetz vibration can be over any surface. You can have any surface be the base, but for us, our surfaces are, it's just the disk. And the way the Lefschetz vibration is defined, for the critical points, see, outside of the critical points, it's basically just a fiber bundle. But in a neighborhood of the critical points, a neighborhood of each critical point, you have these simple closed curves on the generic fiber, which shrink as you get closer and closer to the critical point, and then they collapse at the critical point. And so we call those, when those vanishing cycles is what we call them, when they've collapsed, we call that fiber the singular fiber. And schematically, we represent that this way. So these straight vertical lines just represent a fiber. And then when you have this fishtail here, that represents a singular fiber. And so Akbulut and Özbakçı, and then independently Loy and Perigolini, showed that any Stein filling of a contact structure admits a Lefschetz vibration. And the critical points of the vibration pi give a factorization of the monodromy of the abstract open book into positive right-handed Dane twists. So that's how we go from the Lefschetz vibration, or that's how we go from the Stein filling to the abstract open book. Is we know that we have a Lefschetz vibration for that Stein filling, and through that Lefschetz vibration, we can get a factorization of the monodromy into positive right-handed Dane twists. And so we're coming up on the result we use. So Wendell showed that if you have a planar open book decomposition of a contact manifold, so again, that means that the open book is a disk with n holes removed, then every strong symplectic filling of that contact manifold is symplectic deformation equivalent to an allowable Lefschetz vibration compatible with your open book for the contact structure. And the corollary of that is that if your contact structure is supported by a planar open book, then it is Stein fillable if and only if phi is isotopic to a product of positive Dane twists. And so the result we're using here is Stein fillings of contact structure supported by this planar open book are in one-to-one correspondence with positive factorizations of the monodromy. And I should say it's one-to-one correspondence up to certain equivalences. Okay, and so that right there is where we'll end the big picture, and we'll be using that result that I just stated to classify Stein fillings of universally tight contact structures on LPQ.